Digital logic can become difficult to map as circuits grow in complexity. However, every network of gates can be reduced to a single consistent logic path by using formal algebraic rules. Take the expression shown here, the inverse of the quantity not A and not B or not C. Our objective is to simplify this statement to its most efficient form. This process requires the application of Boolean algebraic theorems. These are established rules that allow us to rewrite the structure of an expression while maintaining the exact same logical output. The first is the distributivity theorem, allowing you to distribute a variable across a group. X and the quantity y or z becomes x and y or x and z. The dual version allows for the same distribution using or and operators. Understanding these baseline rules is the necessary first step towards simplifying the original expression we presented at the start. To handle inverted variables, we use DeMorgan's theorem. The first formula states the inverse of x and y equals not x or not y. Its dual, on the right, shows the inverse of x or y equals not x and not y. We can prove this using perfect induction, which involves testing every possible input state. The truth table shows that the output for a NAND gate is identical to an OR gate with inverted inputs. The same induction method proves the dual theorem. By checking all 4 input combinations, we see that an inverted OR gate yields the same truth value as an AND gate with inverted inputs. This rule scales to generalized expressions involving any number of variables. To find the inverse of a multivariable group, you invert each individual term and swap every AND operator for an OR and every OR for an AND. Distinguish DeMorgan's theorem from duality. Applying duality results in a completely different logical function, as the red text indicates. DeMorgan's theorem, however, maintains mathematical truth. Its equations can be directly substituted to simplify circuit logic. Beyond inversion, we use theorems designed to reduce the number of variables in an expression. This is the uniting theorem and its dual. In this proof, we start with x and y, or x and not y. Applying distributivity, we factor out the x. Since y or not y is always 1, the expression reduces to x and 1, leaving us with just x. The elimination theorems remove redundant terms when a variable and its inverse appear in different parts of a statement. The proof shows expanding the terms creates a combination evaluating to 1. This eliminates the inverted variable, leaving a simplified result. Uniting and elimination theorems remove unnecessary logic gates, resulting in hardware designs that use fewer components and operate with lower latency. The consensus theorem is an advanced rule used for further reduction. Note the highlighted y and z term. In the simplified version on the right, this term is removed entirely. To prove this algebraically, multiply the y and z term by 1, then substitute that with x or not x. Distributing and grouping the terms allows us to apply the null theorem. This reduces the expression, proving the y and z term was redundant. This works because the consensus term, formed by combining terms that contain a variable and its complement, does not affect the final output. If the consensus term is true, the rest of the equation is already true. If it is false, it has no effect. Finally, we use the expand theorem for multiplying out expressions and the factoring theorem for grouping them. With these theorems established, we can systematically dismantle complex expressions. Returning to our initial problem, we apply these theorems to simplify the inverse of the quantity not A and not B, or not C. First, we apply DeMorgan's theorem to the outer bracket, changing the OR operator to an AND. Next, we apply DeMorgan's theorem again to the first term. This flips the internal AND to an OR, leaving double negations. Since double negations cancel out, the expression resolves to the quantity A or B and C. The systematic application of these theorems reduces a complex expression into its most efficient form. This process allows for the optimization of logic gates, resulting in a more direct hardware implementation.
Thanks for watching. See you next time.